All right, welcome back. In this video, we'd like to study the behavior of reverse saturation current. We already mentioned, that reverse saturation current is essentially this, which is coming out of, the expression. Like for example, if you write the total current is going to be Js into exponential QVA by KT minus 1, right? So when VA is negative, it's going to be minus Js, and that's what we are showing here. Essentially, minus Js is the current. But let's try to reconcile. Okay, in the forward bias, we said that diffusion current is dominant, and that seems to be okay, right? You have, as you increase the applied voltage, there's a greater amount of diffusion, and you see greater amount of current flowing. But if you look at the reverse bias, here we said that drift is dominant. Drift current. There is no diffusion because there's a barrier, right? When the drift current is present, the drift current expression is, if you just take electrons, Jn drift is going to be equal to Qn mu n times electric field, right? And as you apply electric field, as Va is increased in reverse bias, what do we expect? The depletion width is going to increase, right? W depletion is going to increase. And essentially, what is electric field? Electric field is simply V applied divided by the width, right? That's the, it's not exactly this because we know the functional form, right? It's an integral. You have to take the charge density and you have to compute the integral, right? So as the width is increasing, the electric field should increase, right? Electric field, the peak electric field will definitely increase. So as you go further and further into reverse bias, the electric field is increasing, but the drift current seems to be constant, right? You get my drift essentially, to pun its drift. So essentially what we are saying is, as you increase the reverse bias voltage, the depletion width is increasing. That means peak electric field is increasing. Even though electric field is increasing, it seems that the drift current is constant, which is a very strange thing, right? We never see that, whenever we studied the drift current, you saw that the drift current was proportional to electric field. If the electric field increases, the drift current increases, right? That's what we have seen in the simple semiconductor cases. Now it is something different. And it's kind of a puzzle. I want you to think about it, what is happening here, okay? If you have thought about it, to answer this puzzle, you have to understand how the minority carrier profiles look like, okay? So we have seen this multiple times. So essentially in forward bias, your minority carrier profile is going to be like this. What happens in reverse bias? How does the minority carrier profile look like? If you simply plug into the equation here, so if VA is negative, right? VA is equal to minus VR, let's say something. You apply a negative voltage, this term is going to go to 0. So the minority carrier density at Xn is going to be minus P0. Okay, so this is going to be essentially 0 because this is your Pn if you take it. So this is your Pn naught, and you subtract Pn naught from it, you're going to get 0 at x equal to Xn. Similarly, here you're going to get 0. So what does it mean? It means that instead of having excess minority carriers, we have deficit of minority carriers. Minority carriers are being removed. And why are they being removed? Well, look at the electric field. Electric field direction is this, right? From N to P. So happily, your minority carriers holes will travel. So P will, holes will go in this direction. Electrons will go in this direction. So the minority carriers, whatever are present in the N and the P regions, they're going to be swept away across the depletion region. So we are creating deficit of minority carriers. What happens when you have deficit of minority carriers? Well, always remember, semiconductor is going to try to come back to equilibrium. If you have excess minority carriers, they will recombine and come back to equilibrium. If you have deficit of minority carriers, it's going to generate and come back to equilibrium. Equilibrium is something that nature loves, right? So we always try to come back to equilibrium. So how does the profile look like for in the reverse bias? The minority carrier profile is going to be exponentially increasing. The same diffusion length, LP, is going to be there. Okay. So over a few diffusion lengths, the minority carriers are going to come back to equilibrium. Similarly, on the electron side, they're going to come back to equilibrium. Sorry, on the p side, electrons are going to come back to equilibrium after a few diffusion lengths. Okay. So, can this explain our dilemma? Well, it does. In the reverse bias, the important thing is not really the electric field, but the number of carriers that are important. Okay. So I have kind of deliberately not emphasized. So Jn is equal to be Qn mu n electric field. I talked about this. I said that this is going to change. Okay. Changes as V applied increases, right, in the reverse bias. But what happens to this guy? Okay. This is dependent on material properties. What is the diffusion length? What is the doping? And all that, right? Everything is interrelated. Essentially, this depends on material properties. And so we see that in reverse bias, the current is actually limited by the availability of minority carriers. Okay. J in reverse bias, current is limited by availability of minority carriers. Where minority carriers at the edge of the depletion region. As many electrons, as many minority carriers are present, those many of them will be swept across the depletion region. Electric field is sufficient to sweep them off, but we are going to be limited by the number of carriers. Okay, that's why in the reverse bias the current is constant. Okay, so this is a very subtle point, but this is important to consider. Okay? Let's try to solve a small problem. Well, I mean, I'm not going to fully solve it. This is from the example from the textbook 8.2. The solution is given, so I would like you to go back and do it by yourself. But let's just walk through the procedure right now. Okay. So we are given a semiconductor with Na and D is equal 10 power 16. Ni is given. So diffusion coefficients are given to you, and then taus are given to you. The lifetimes are given to you. Okay. So you are asked to calculate the reverse saturation current density. How much is it? Okay. Well, that's going to be dependent on. We have to calculate the numbers, right? So J S is basically Q dP. So we are writing the P term first. So dP Pn naught divided by Lp plus Q dN Np naught divided by Ln, right? And now in this particular problem, we are given Na and Nd are same, right? So I'll write Np naught equal to Pn naught equal to Ni square divided by 10 power 16. Okay, okay, I mean, it's a simpler problem. So I'll actually take the correct number and I'll say that this is equal to 2.25 into 10 power 4. Okay, I didn't make an approximation now. Okay, because denominator is 10 power 16, it's an easy number. Okay, so now what happens? How do you compute? So this is going to be equal to Q times the NP naught is going to be, NP naught and Pn naught are going to be 2.25 into 10 power 4 into dP by Lp. dP is given to us. What is Lp? Well, Lp is not given, right? The diffusion length is not given. But remember, Lp is going to be root of dP tau p. So I can in principle write this here itself. I can make it tau p and then I can write a square root, right? dP by Lp is going to be square root of dP by tau p plus square root of dN by tau n. Okay, so you can calculate it. I'm not going to do it. So, well, the order of magnitude, let's try to see what it is. So this is going to be 10 power minus 19. This is going to be 10 power 4. So, okay. This is going to be 10 power 4. dP is 25. Square root of 25 is going to be, 5. and then let's say tau p is given as 5 into 10 power minus 7. So 10 power minus 7 square root will be 10 power 3. So this will be something on the order of 10 power minus 3, I think. This also is going to be all same order. So essentially the brackets is going to be of the order of 10 power minus 3. Okay. So, oh no, 10 power plus 3. 10 power plus 3. Because 10 power minus 7 square root in the denominators plus 3 on the top. So essentially it's going to be something of the order of 10 power minus 12. Okay. Amps per centimeter square. So always remember this is a typical number. So saturation current densities, typical Js, order of picoamps per centimeter square. This is per unit area, please remember that. We are looking at the cross section. Okay. So this is how you can calculate. So please make sure that you put in some effort and try to calculate these numbers. It's going to be useful for you. Okay. And then with that, we can essentially sum up what are the different currents in a PN junction. So if you look at the various contributions, we saw that at the edge of the depletion region, you have the diffusion current, which is going to be dominant. And as you go deeper into the semiconductor, the diffusion current is going to reduce. As you go into the N-type semiconductor, the P-type semiconductor is going to reduce, right? And as the holes are reducing, number of electrons is increasing. So essentially, this was a minority carrier current which was reducing, and that is being substituted by the majority carrier current, which is basically the electrons. Okay, electrons flow in to supply recombination with holes. Right. So the diffusion is providing only holes. Electrons have to come in. Electrons will come in from the N-type semiconductor, so the majority carriers. So as you go deeper into the semiconductor, you will see that the majority carrier current is picking up. Okay. And similarly, on the P side, at the junction you have the diffusion current, which is there. But as you go deeper into the P-type, the majority carrier holes will be supplied by the P-type semiconductor, so that is dominant. So overall, one important rule that can never be broken is that the total current is constant, or rather uniform, right? Because you're not having any other source or sink of current. So essentially, whatever is coming from the left has to go into the right. Only the distribution changes. In the quasi-neutral regions, you have the drift current which is dominating. Okay, it's a majority carrier drift that is dominating. But along at the junction, it is a diffusion of minority carriers that is dominating. Okay, so please take a moment, look at this diagram, and try to draw it by yourself. Okay, when you do that, you will see that there are a lot of assumptions that are here, which are kind of not mentioned, but you will see that how they are coming into picture. All right, so this is about the total current. Let us try to answer one more puzzle. I'm not sure if you have thought about it. So what I'm saying is here, in the quasi-neutral regions, majority carrier drift is a main contribution, or main or only contribution actually. Contribution, right? So we come back to the same problem. What is drift? Drift is going to be Jn n Q, is equal to Q times n times mu n times electric field. In the quasi-neutral region, n is constant. This is constant, isn't it? And mu and Q are material constants. And we assumed, remember, we assumed E equal to 0 in quasi-neutral regions. When we are drawing the band diagrams, we said E is going to be 0. Is it really true? Because there's some current, right? And of course, it's a uniformly doped semiconductor, so there is no N changing, there is no Q changing, there is no mu changing, so there is going to be some electric field. Okay? So we would like to compute the electric field also, and that is what is done in this problem. I will leave it to you as homework. The solution is there. Please go and understand the problem. So essentially here they're asking you to calculate the electric field in the quasi-neutral region. Sorry. The electric field in the quasi-neutral region. How will you calculate that? Well, you will estimate the total, first you will calculate Js, okay, Js, right, saturation current, and then calculate J is equal to Js exponential, there's some voltage given to you, right, here. So voltage is given to you. So exponential QV applied divided by KT minus 1, okay. So how much is this going to be? Let's assume, okay, I'm not computing exactly, but just doing a back of envelope calculations. So this is roughly, we said 10 power minus 12 picoamps, 10 power minus 12 amps per centimeter square. So picoamps into exponential QVA is 0.65 divided by KT, it's room temperature. So KT is 0.256, right? So 25, 4, 6, 24, it's supposed to be minus 1 here. So this is going to be close to 10 power minus 12 exponential 65 divided, 0.65 divided by 0.0256 is going to be 25 into 6 plus 26, okay, plus 26, okay. So you're going to have some number coming out here, large number, which is going to compensate. Eventually, you will see that this is going to be some amps per centimeter square. Let's say 1 to 10 amps, 1 amp per centimeter square approximately. Okay, so this is going to be the current, total current that is flowing through. Remember, the Js was only picoamps per centimeter square, whereas the total current, diffusion current, is going to be amp per centimeter square. So 12 orders of magnitude higher. That's the scale we are talking about. Okay, so if you have 1 amp per centimeter square, what is the electric field? Well, Jn was Qn mun electric field, right? So now we said this was 1 amp per centimeter square. This is given by the doping. I don't know what is the doping. Oh, well, okay. They asked you to take it from another example. You just look up. It will be something like 10 power 15, 16 something, okay? Approximately 10 power 16 you take. This is some, 1400, 1350 centimeter square per volt second. What is the electric field? You compute, okay? You have everything given to you. So you will see that this is going to be approximately some 1 volt per centimeter, kind of, few volts per centimeter, okay? That is going to be the range. So there is a very small electric field, okay? So this is insignificant when compared to E field in depletion region. How much was it in the depletion region? Remember, E depletion was 10 power 4 volts per centimeter. It's reasonably high, 4 orders of magnitude higher when compared to the electric field in the quasi-neutral region. And that is why we can make that assumption. That assumption is still correct. It's not wrong. Whatever band diagrams we have drawn are not wrong. It just ignores the minor point that there is a small electric field across a quasi-neutral region, not a large electric field. Okay. Well, it is also possible because it's kind of plausible because it's a semiconductor, right? Semiconductors are going to have some, they have finite resistivity. They are not like metals. In metal, we say that the electric field is purely zero because they have huge carrier density. Okay, then electric field, even there it's going to be a small thing, but it will be negligible, right? Okay. So Yeah, with that, I would like to stop this discussion on the reverse saturation current. In the next lecture, we will talk about capacitance, how the depletion capacitance changes. So we'll see that there is certain depletion capacitance associated with a PN junction. And then we'll also talk about a few non-idealities in a PN junction device. All right. So that's it for now. Thank you very much for your attention. I'll look forward to seeing you in the next lecture. Bye.